Thank you so much. All right, so let's start. Hello, everyone, and thank you so much for joining us today for this month's Grundfest Memorial Lecture. So it's been a few months since our last lecture as we paused for the summer break, and so it's doubly exciting to be back and very excited to have such a great lecture to start off with this academic year. I'm sure you're all very excited as well, so I'll keep this part really short and we can dive right into Dr. Sun's lecture. So I'll just start off with some beginning notes. So as Achyuta mentioned, we'll start today's lecture at 12:05, or I guess 12:06 now, and we'll try to go until 12:50. Also, just some administrative notes. If you'd like to follow future speakers and schedules, please do follow our webpage as mentioned here. And you can also follow us on Twitter for the same schedules and uh, lecture speakers and so on. But anyways, so typically before we start off with the lecture, we always give a brief description of uh, who the lecture is named after and the significance behind that for for people who are new to the lecture series. So Professor Warren Grundfest was a professor at UCLA, and he was an SPIE fellow in biophotonics. But most importantly, from our context, he was a great advocate of junior scholars, and that sort of slots in with the motto of this lecture series of trying to give a platform to junior scholars, late stage PhDs, uh, to platform their brilliant work. Uh, and just quick shout out to my co-organizers, Professor Achyuta Kadambi at UCLA and Professor Katie Bauman at Caltech. Thank you so much for all the help. And yeah, it's great to be organizing this lecture series along with you all. I'd also like to mention our sponsor, Akasha Imaging. And they have very graciously agreed to sponsor an inverse honorarium, which means we essentially give a small monetary incentive for non-permanent speakers, which are PhDs and postdocs, to sort of portray their work and give them this platform. And so, big thank you to Akasha Imaging for sponsoring this. And with all that being said, I finally arrive at introducing our speaker today, Dr. Sun, and I'm very excited to do so. Uh, Dr. Sun will today talk about his work in computational astronomical imaging and his work that takes forward uh, the very widely known and amazing work on imaging black holes and truly imaging the invisible. And so I'll not take too much time at all, and I'll pass the mic to Dr. Sun, and really looking forward to your talk. Thanks so much.
Okay, thanks for your kind introduction. Let me share my screen. Can you see my slides? Okay. Yeah. Okay, let's start. Hello, everyone. I'm He Sun from Caltech. I'm very honored to be here today to share my research on computational astronomical imaging, especially some recent developments of machine learning-based inference and the sensing algorithms for future black hole observations. I guess I don't need to emphasize too much about the importance of imaging for the audience today. As we all know, imaging technology plays a critical role in many scientific fields, such as astronomy, biomedicine, and material science. Until now, we can say imaging has become one of the most important sources of scientific data nowadays. For example, according to a study from IBM Research, images approximately make up more than 90% of all medical data today. And in astronomy, this number could be even larger. Almost all the astronomical data are derived from telescope observations. As science continues to push the boundaries of our human knowledge, new scientific goals also bring unique challenges that require us to improve the imaging capability in extreme conditions, such as extreme timescale, extreme contrast, or for the super resolution microscopy, extreme resolutions. Traditionally, these goals are typically achieved purely by improving the design and manufacturing of imaging hardware. I'm from a background doing astronomical telescope-related approach. For example, to improve the resultant power of astronomical sources, the most recent NASA's flagship space mission, the James Webb Space Telescope, has an aperture that is 3 times larger than its famous precursor Hubble Space Telescope. However, due to the limitation of the current rocket, the large aperture of JWST has to be designed segmented so that we can fit the telescope into the space vehicle first, and then launch and deploy the telescope in space. This actually led to unexpected technological difficulties in manufacturing. Since the JWST was initiated in 1996, it has been plagued by numerous delays and cost overruns. Until now, its launching time has been delayed for more than 14 years. So some astronomers always kidding that it should be named the Just Wait Space Telescope instead of James Webb Space Telescope. This example has shown us that purely upgrading the hardware to meet the technological specifications can be prohibitively expensive and inefficient, not only for the telescope, but for many other scientific imaging missions. To bypass the hardware limitations, nowadays imaging scientists have started to integrate advanced computational algorithms as part of the imaging pipeline to improve the system's imaging capability. One recent and well-known example is the Event Horizon Telescope. Although it is impossible for us to build an Earth-sized telescope, we can actually link the radio telescope across the globe to form a synthetic telescope, and then use interferometry and signal processing technique to extract hidden signals from these telescope measurements. And using this approach, the Event Horizon Telescope collaboration published its first black hole picture in 2019. This innovative idea, as we all know, is just called computational imaging. From my understanding, computational imaging provide great opportunities to revolutionize scientific imaging mainly in these 4 aspects I listed. For example, first is hardware. 2 basic building blocks of a computational imaging system are the hardware and the inference algorithm. Because in computational imaging, we first collect data using the hardware instrument and then recover the hidden signal from the data. Since the inference algorithm can enable us to extract information from noisy and non-traditional measurement data, our design of the imaging hardware now can become more flexible, and we can use low cost and portable hardware to achieve high quality imaging. For example, one instrument I'm working on is the integral field spectrograph. You can understand that as a multiplex spectral broadband camera. By combining the lensless array and the prism, we can use a very cheap hardware to achieve very high quality, high resolution multispectral imaging. That's hardware part. And the second definitely is the inference. The inference will enable scientific imaging system to overcome physical limitations and achieve precise observations impossible with traditional method. For example, we can do super resolution imaging. And also inference will help us improve the interpretability of the scientific discoveries by quantifying the uncertainty of reconstructed scientific imaging statistically. In addition to these 2 basic aspects, computational imaging also to some extent grants the next generation scientific imaging system more intelligence. For example, by optimizing the data acquisition policy or the sensor placement in the imaging system, we will be able to collect more information, more informative data with low expense and time budget. And also control system, by introducing control systems such as adaptive optics in the telescope or microscope, we can isolate the scientific imaging instruments from detrimental environmental disturbance, allowing the instrument to perform more robustly in different conditions. In my past research, I've been very lucky to work on developing new imaging techniques from all these 4 aspects, especially their applications in astronomy and biomedicine. Today, I want to highlight 2 of them that are related to black hole observations, respectively, the deep learning-based uncertainty quantification method for image reconstruction and a framework for the co-optimization of the imaging hardware and the reconstruction algorithm. For the convenience of illustration, today I'm going to be introducing this work mainly in terms of black hole imaging. However, I want to emphasize first that this work can be easily generalized to other computational imaging applications, such as medical imaging problem. I will also briefly show some examples in the later part of my talk. Okay, let's first dive into the first part, uncertainty quantification for black hole imaging. Black hole imaging is an interferometric imaging task in the Event Horizon Telescope. By correlating the data from each two separate telescopes, we will get a single data points, which corresponds to the frequency components of image. The location of the data points in the 2D third domain is related to the length and orientations of the baseline connecting two telescopes. So since the Earth is rotating over the night, after several periods, we will collect several frequency components that spread the whole third domain. So using this collected sparse frequency domain measurement, we can run reconstruction algorithm to recover the hidden signal. And that's how we achieve the image of the first black hole picture. Similar to many other computational imaging problems, the hidden black hole image is typically solved using a maximum a posteriori estimation method, or so-called map estimation method. In map estimation, we maximize the log posterior distribution of the hidden image, conditioned on the measurement data y to get a solution. According to Bayes' rule, this loss function can be actually further expanded as a summation of the data likelihood and the image prior distribution. So the solution to this optimization problem will not only fit the measurement data, but also satisfy some image properties defined by the prior information or regularizers, or so-called regularizers, such as the image sparsity or image smoothness. And this map estimation method will help us get reasonable solutions, even if the reconstruction problem is ill-posed, like the black hole image reconstruction. However, although that sounds perfect, one fact we should not neglect about map estimation is that it only produces a single point estimate without any measurable uncertainty or confidence. This can be a serious limitation, especially when we are dealing with scientific data, because in reality, image reconstruction problem could have multiple reasonable solutions considering the measurement sparsity and the measurement noise. For example, when the Event Horizon Telescope was trying to take the first image of black hole M87, scientists find that many images could fit the radio interferometry data we measured equally well. As you can see in these slides, although from these different pictures, we all clearly find a ring structure with almost same diameter, it seems like that there are a lot of uncertainty about the flux distributions on these rings. However, in order to deliver reliable scientific interpretations of black hole, we have to accurately quantify and understand the confidence of different regions of these reconstructed black hole images. That is not simple. It took astronomers from ngEHT several months to finally investigate all the possible reconstructions and finally compiled this reconstruction mean and standard deviation of the first black hole image. In this case, instead of recovering a single image from the measurement data, we need to estimate the full posterior distribution of this image reconstruction problem. Traditionally, this could be achieved using sampling-based methods such as Markov chain Monte Carlo method or etc. However, as widely known, the sampling-based posterior estimation method can be prohibitively slow and computationally intensive for high-dimensional images because of the curse of dimensionality. That's the background for our deep probabilistic imaging research. In order to achieve computationally efficient posterior sampling. Recently, we developed this deep probabilistic imaging algorithm, or so-called DPI algorithm, where we try to learn a deep generative model to approximate the posterior distribution of an image reconstruction inverse problem. Since training a deep generative model is an optimization-based approach, it is much more efficient than traditional sampling-based method because in traditional sampling method, a lot of computational time is wasted on exploring and rejecting less possible samples. However, as a comparison in DPI, it conducts a gradient guided posterior exploration, which is much more efficient. The key components of DPI to make it work is the deep generative model. In the past few years, we witnessed the great success of deep generative model in computer vision field. For instance, given enough training images of background pictures, as shown in these slides, we can easily train a neural network that takes a variable of noise Z as input and output a picture X that looks like a real background image at the first glance, but it's actually non-existent. By plugging in different noise, the neural network will provide different output pictures. So this learned generative model implicitly defines a complicated distribution of the background pictures. This provides us a very powerful tool to approximate the image posterior we want to achieve in DPI. In DPI, we hope that we can do something similar. We want to train a deep generative model that can also generate a complicated distribution, which looks similar to the posterior distribution we want to solve. Every time we insert some noise to the neural network, we hope that we can get an image that is equivalent to samples from the image posterior distribution. And then we can say we get the fast and accurate posterior estimation using this deep generative model. That sounds like a great idea, right? However, one remaining question we haven't answered here is how could we train this neural network? Unlike in the case of training a generator of background pictures or a generator of human faces, in our method, we don't have a training set of multiple images we can use to learn the neural network base. If we had the training set of posterior image samples, there are no need to learn this neural network, right? The only data we have for optimizing this neural network is the sparse and noise measurement data of a single hidden image, which is same as the case of map estimation. So here in DPI, we instead of using a collection of training images to solve for the neural network base, as is typically done in other computer vision problems, here we define the loss function of DPI as the chaotic divergence between the neural network defined distribution and the true image posterior. The chaotic divergence is a statistical matrix to measure the similarity between the two distributions. So by maximizing this loss, we force our generative model to approximate the true image posterior. This makes DPI a special type of variational inference method. In variational inference, we first define a family of density functions, Q theta, which is visualized by the blue space here in the current slides. And then we solve an optimization problem to find the parameter theta star that can best match our density function, the parametric density function, to the target posterior distribution Px given y, which is shown by the which is denoted as the yellow star here. Traditional variational inference algorithm could be easily limited by the capacity of the variational models if we assume our image posterior follows a Gaussian or some mean field distribution. However, in DPI, we define a very flexible family of distribution using the generative model. So we can better capture the complicated image posterior distribution via interesting targeting, and it usually get good results. Okay, that's the basic idea of DPI. But one last thing I want to mention about DPI is that we can also use different divergence laws at object function in our training. Before I introduce the chaotic divergence as commonly used laws in the variational inference. However, usually it is not the best one to model the similarity between two distributions because it is an asymmetric divergence function, which means that the KL divergence between Q, theta, and P, and the divergence between the P and Q theta is not equal to each other. This sometimes will lead to a zero forcing effect in our neural network training, meaning that the variational models tries to avoid including samples from less posterior probability regions, which will cause mode collapse issue. Our recent study showed that alpha divergence could be a better choice for DPI loss function. Alpha divergence here is a broader class of divergence metric which has a tunable parameter alpha. I won't dive too deep into the math here, but one key message I want to pass to you, since the alpha divergence can be symmetric when alpha equals to 0.5, it can better capture the multimodality in the image inverse problem posterior distribution. Okay, let me show you some examples or experiments we've run on DPI. This is an example of a synthetic black hole observation data. The left image is the ground truth image we used for simulating our observations. And after training, our deep generative model could produce the image samples shown on the right-hand side. You can see that our learned network captured a posterior distribution that indicates there are two different modes in our data. We did some analysis afterwards, although one of them does not look like the ground truth image as shown in the right boxes. Both image modes fit the data and the image prior very well and belong to the true image posterior. This example has demonstrated that the DPI method could learn a complicated image posterior, even those multimodal cases that's hard for the sampling-based methods. And we also run DPI on several real data. This is an exciting result we got when we run the approach on the original data set that is used for reconstructing the first black hole picture. It's really encouraging that if we compare the DPI identified standard deviation, the right figure, to the standard deviation figure reported by the original black hole imaging paper, you can see that these two images are amazingly similar. In both uncertainty map, we recovered and the report in the first paper, there are three regions with the highest uncertainty that seem to match up. However, it only took DPI around 1 hour to train on a single GPU to get this approximate posterior distribution, which is much more efficient than the ad hoc uncertainty quantification methods used by ngEHT originally, which took several months. So we believe DPI is a fast and reliable uncertainty quantification tool. And we are actually working on using this method to understand the uncertainty of many other astronomical imaging data right now. Okay, that's the first topic I want to present. By optimizing a deep generative model to approximate the image posterior, we can achieve efficient and reliable uncertainty quantification in image reconstruction. Image reconstruction is definitely important for us to better interpret the measurement data. However, another important thing we need to keep in mind is that the quality of our reconstruction also depends on the information that is included in the measurement data. So the optimization of the sensing policy or the design of the imaging hardware is also important for us to collecting more informative data for computational imaging reconstruction. Back to our black hole problem. In our future black hole observations, we would also like to improve our K-space, improve our frequency domain coverage by introducing new telescopes into our telescope network. However, due to the expensive cost of each new telescope, these site locations need to be carefully selected before we really move to the construction. This is a sensor placement problem for computational imaging. Typically, people can solve this problem using compressed sensing theory. However, for the event horizon telescope, which is a nonlinear imaging system that is influenced by complicated measurement noise, it is impossible for us to optimize the telescopes using some analytical methods. In this case, to efficiently tackle this new telescope placement task, we recently adapted the idea of end-to-end computational imaging system design and jointly optimize the imaging hardware, which is the telescope set locations, and our telescope and our black hole reconstruction method. Rearranging the blocks of the previous slides, it's not hard to find that the black hole imaging pipeline is very similar to an autoencoder, just like other computational imaging system. So we can easily adapt the end-to-end design approach to jointly design our imaging hardware, which is the encoder in our system, and the reconstruction method, which is decoder in our computational imaging system. However, one special thing for our black holes imaging is that our task is constrained very differently from many other computational imaging design problems. Actually, in our system, we don't have the freedom to arbitrarily place the telescope on the Earth. Instead, astronomers have already pre-selected several candidate telescope set locations across the globe based on the weather conditions and many other factors. And we can only optimize our encoder part to select a subgroup of telescopes from these candidate locations. This makes our census design problem combinatorial optimization instead of a continuous optimization problem. In this case, many subgroups of telescope may achieve equally good performance. So we want our encoder can explore all of these different solutions, and ideally try to provide some insights why these different combinations all works, and explain the relationships between different candidate telescopes. This can be a complicated task compared with the continuous optimization. To solve this problem, here we represent our sensor selection strategy, the encoder part, as a probability distribution to explore multiple designs simultaneously. The probability distribution is parameterized by a trainable parameter theta here. And we hope that after we train our imaging hardware encoder, we can get a probability distribution. Whenever we draw samples from the distribution, we can get a new design of the sensor system. And we hope that each design will perform well for our image reconstruction. Unlike in the DP algorithm, here we introduce the distribution considering the physics. So to improve the interpretability of our imaging hardware design, we model the probability sensor selection policy as a binary fully connected IC model, or so-called Markov random field instead of black box neural networks. Since the IC model has some physical meaning incorporated, here each telescope will have an activity parameter, which represents how important it is to include each telescope into the future observations. And each pair of telescope will also have a correlation parameter. If the two telescopes are positively correlated, that means their measurements are complementary. So we may want to include both in our future design. And if they are negatively correlated, that means that their measurements are duplicated. So we probably should only include one of them to reduce the budget we used for construction. This learned IC model helps explain the interaction among sensors. We demonstrate our algorithms on next generation event horizon telescope design under several different assumptions. Here, the left figure shows our candidate set locations across the globe. On the right-hand side is a set of learned IC model parameters considering only thermal measurement noise. Since the thermal noise has a Gaussian distribution, so we partially understand what the optimal design should be in this case. The top figure shows the activity of each telescope, and the bottom figure shows the correlations between each pair of telescopes, where the right pixel represent the positive correlation between two telescopes, and the blue pixel represent the negative correlations. Our model successfully learned the strong negative correlation between two powerful co-located sites, the SMA and GSMT telescope, both in Hawaii, and ALMA and APEX telescope, both in Chile. This means that the co-located sites will give us approximately same measurements if we assume only simple noise, which makes a lot of sense. So from this example, we demonstrate that our algorithm can reproduce the known designs reasonably. But what is more interesting for us is to use this method to recover the sensor design in cases where we don't know what to expect. We recently used this framework to investigate the telescope selection under more realistic atmospheric turbulence. And it's really exciting to see that the site activities and correlation maps change a lot given this new noise assumption. The top row is the result I copied from the last slides, and the bottom row is the result we got when we assumed there serious turbulence caused by the atmosphere. As you can see, here we find the two closely located telescopes, LMT and OWL, which are negatively correlated before, now become positively correlating. This suggests that although the short baselines are not important with Gaussian noise, they can be very important under the case with atmospheric turbulence, because they can help calibrate the contaminated phase infos when we're doing the black hole reconstruction. Although this is very preliminary result, I'm really excited that this sort of thinking for the first time help us understand the next generation event horizon telescope design with realistic noise. And this has never been quantitatively studied before due to the fundamental analytical difficulty. We are currently working with astronomers from Harvard and MIT to use this algorithm to design, to select from more than 50 candidate telescopes across the globe for our future observations. Okay, that's the second story I want to introduce. In summary, I first introduced your DPI that try to optimize a deep generative model for efficient image uncertainty quantification. And then I talk about how to optimize the telescope placements by combining the interpretable physics model and the machine learning. From this project, I hope that I can give you a taste of how computational imaging can help us improve the future black hole observations from the inference and the sensing side. However, as I mentioned at the beginning, although I mainly discussed this project in the context of black hole imaging, this method are never limited to this specific example and should be applicable to many other imaging modalities. For example, one similarly orthogonal but actually very related problem is the undersampled MRI. Similar to the Event Horizon Telescope for black hole imaging, in MRI, the scanner also measures the sparse frequency components of a target, and we then run the reconstruction method to recover the hidden image. So because of the similarity of the measurement data's physics meaning in both cases, all the work I've talked about can be easily applied to the undersampled MRI problem. Simply replacing the sparse ngEHT measurements with undersampled MRI scanning, we can train a generative neural network using DPI to quantify the uncertainty of reconstructed MRI image. I won't dive deep into the applications due to time limit, but as you can see, the DPI estimate a standard deviation map, which is shown in the middle, very well captured the profile of the reconstruction absolute value, the reconstruction absolute error, as shown in the right figure. And similarly, the co-design framework can also be used for designing the best frequency space sampling pattern in MRI. So we can reconstruct high quality MRI images with limited scanning time. Actually, since MRI is more flexible compared with the telescope placement, recently I'm also working with two junior students, Ray and Tianwei in our group, to extend our framework to achieve sequential code design. Basically, here we wish to build an MRI system with intelligent active acquisition, where we can use past measurement data we collected and the corresponding preliminary reconstruction to decide the future MRI scanning pattern. This approach will define a closed-loop control system that improves the efficiency of the computational imaging data acquisition. More specifically, in each loop, we first collect measurement based on some scanning pattern, initial scanning pattern, and then we preliminarily construct the hidden targets based on the current measurements. And once we got the current measurement and the current reconstruction, we can decide the sampling patterns for the next control loop based on this information. Since we continues to adjusting our acquisition pattern based on our knowledge up to now, this should help us acquire more informative data and finally get better reconstruction. We've tested our method in two different scanning scenarios, the 1D light sampling, 1D light scanning, and the 2D point scanning, and also using the NYU fast MRI data set. This is the results we recently got for our sequential MRI code design reconstruction. By comparing the SSIM of our reconstruction and with other benchmark case, we found that our method achieved the best performance. And this can be also visually recognized in the zoomed part. For example, in the orange region, other benchmark cases sometimes introduce some artifacts in the image, but our method performs pretty well. And I think this case is more interesting to see. Here we try to visualize how our algorithm gradually adapt a sampling pattern based on the past measurements. These four columns represent the four different steps where we do our adaptive sampling. You can see when we try to image the targets with different orientations, actually our method can gradually adapting a sampling pattern based on the important features in the image. This is a pretty realistic case because in MRI scans, mostly a patient will not align the body perfectly to the MRI machine. Since our algorithm can successfully learn the patient's orientation and gradually adjust its scanning pattern to collect the best data, this will significantly improve MRI reconstruction quality. Okay, that's all I want to talk today. Let me wrap up my talk. As I said, introduced, I mainly present two works. Two projects I've been working on, respectively on the image uncertainty quantification and using generative model and the co-design of the sensing and inference algorithm. And from these examples of black hole imaging and MRI, we can see that the computational imaging method can significantly improve our future scientific imaging system. I feel so happy to be part of the computational imaging community because I think computational imaging has provided us great opportunities to revolutionize our future scientific observations. I always want to, I always would like to conclude my talk with sayings from a great Princeton physics Freeman Dyson. He said new directions in science are launched by new tools more often than by new concept. I think with the help of computational imaging, we will definitely redefine the way we observe the world. And hopefully by defining new computational imaging techniques, we can make contributions to the new science of the next generation. Yeah, that's all about my talk. I'd like to thank all the collaborators and my advisors. Thanks for the listening.
Thank you, He.
Yeah. Yeah, I can take any questions about black hole imaging, MRI, and our algorithm.
Yeah, so there seems to be a question in the chat from Professor Goyle. Do you see it?
Yeah, I'm reading.
Maybe it's good to read it out loud though.
Sure, yeah.
Sorry,
So the question from Vivek is pertains to your DPI work. So notes first of all that would like to read the paper in more detail, but beyond that, the question is, would you please discuss the dimension of Z and its significance for the results that you obtain?
Okay, sure. Let me go back to the DPI slides so that we can have more discussion. Actually, a quick answer to that question is that the hidden state Z has exactly same dimension as the image you want to recover, because here we use a special type of generative model called normalizing flow, which is a type of invertible neural networks. The reason we want to use that generative model is because in our KL divergency, we not only need to do the forward pass to do the image generation, we also need to do the backward pass to evaluate the probability of the image to compute the stochastic form of the probability entropy. So that's why we finally decide to use the normalized flow, which has same dimensions in its noise space and the image space. Yeah, but that's really a good question. I don't know whether that answers your concerns.
Okay, so I think if Vivek wants to respond, he'll respond in the chat. So let's move on to any other questions that are there. Anybody else have questions? Emma?
Yeah, if I can just jump in, great talk, thank you. I think the most exciting part for me was where you were able to actually predict, like, oh, you would think from a simple noise model that you shouldn't use this telescope, but actually it's the other way around. And so I guess I just wanted to sort of put that into like a physical intuition. So I have two little questions, and I guess the first is it true that the redundancy is sort of, it becomes helpful because of this closure technique that you do to deal with turbulence? So like some kind of redundancy is good?
Yeah, is that your first question? Yes.
Yeah, that's the first question.
Yeah, actually, maybe we can think of more common case like a phase retrieval. In phase retrieval, like we typically only have intensity measurement, but we don't have the phase information. Although it's a little different from black hole interferometric imaging, it's same physical intuition that we don't have the phase information due to the atmospheric turbulence. So in that case, if we have some redundancy, that will help us calibrate the data collected by different telescopes, especially the short baselines. Why it's important? Because short baselines means low frequency measurement, and for those measurement, the phase is typically small for a natural image, and that we can just assume those to be zero and do some calibration traditionally. But now our method, automatically find this intuition from the training.
Gotcha. Okay, and I guess my second question to just make sure that I'm understanding the constraints on your data. So it makes sense to do this subset if you're budgeting the telescopes, but do you ever have the case where you budgeted and you got this data, which is obviously very precious, but then maybe the weather was so bad that you would want to exclude it? Or is this strictly to sort of to pre-plan rather than to exclude data after you've collected it?
Oh yeah, thanks. That's a very good question. Actually, in our simulator, in our physics simulator, we already take weather into consideration. So basically, we just have a probability like how many nights we can observe during the year. So we have some random dropout in our training, so that's already took the weather condition into consideration. But there are also many other things we haven't considered because, for example, some environmental costs or some other things. Definitely it's not perfect, but we try to throw as many things as possible in our physics simulator to do more reasonable, realistic design.
Thank you.
Yeah, thanks, Anna.
Great. So I think we can stretch just by a few more minutes because we have one more question in the chat. So Yang asks, thanks for the great talk. And in terms of DPI for joint design of acquisition and reconstruction, now for the MRI application, The learned acquisition looks very interesting since in k-space, it only occupies one direction, the horizontal direction. Is the acquisition pattern fixed for all samples?
Oh no, like I think that's a different. I mean, that's something we want to develop. Is that we want to develop a active acquisition, adaptive acquisition sample. So we at the first step, yes, fixed. We always collect the data from the low frequency part, but that's very few data. For most collections, we just gradually, I mean, just decide step by steps based on our up to now data collection. Because from the old data, we may have some rough understanding on the major features in the image, and that will help us decide which frequency components is more important compared to others. So it's not fixed for all the samples. For the first step, yes, but later, like it will adapt based on the true target.
Got it. Understood. So we have a one-on-one afterwards. So I'll save my questions for then. I think that brings us to 12:50. So I think we'll end the lecture here. Once again, let's all thank Heath for the great talk.
Thanks, everyone, for coming.
And yeah, thanks everyone for coming. Until next time. Bye, everyone.
Thank you so much for joining. Bye.